for your invitation at this nice conference. The title of my seminar is Non-Singular Black Holes and Mass Inflation in FR Gravity. This presentation is based on a recent publication to which I gave my contribution with some colleagues of the University of Trento. The recent discovery of gravitational waves from binary systems of black holes or relativistic neutron stars had largely confirmed some of the most important predictions of the strong field regime of general relativity. Sorry. Maybe if I will speak without all this device. Can you hear me? Sorry, I will ask for the last time. Huh?
Yes, I can.
Do you hear? Okay. So, and 2 years ago, the Event Horizon Telescope collaboration also furnished the first imaging of a supermassive black hole at the center of M87. So, on one side, we had some important confirmations on the existence of the black holes, but on the other side, many conceptual problems related to their description still remain. For example, the problem of central singularity, the information paradox, and so on. And in particular, since space-time singularities are problematic, a lot of investigations are dedicated today to viable alternatives to the Kerr metric, which is the vacuum stationary solution of general relativity, which is often used to describe the astrophysical black holes. Another well-known problem related to the Kerr model is the instability which may occur near to the Cauchy horizon. This is the so-called mass inflation problem. Mass inflation seems to be strictly connected with the existence of the Cauchy horizon. However, it's not still clear, it's not still so clear a priori if it also occurs in the absence of central singularity, for example, in the regular black hole solutions where we have a de Sitter core. And in this respect, recently some papers appeared. You can read the reference in this slide, where the problem of mass inflation in regular black hole solutions is investigated, and the question, the problem is still open. In this seminar, I will speak about mass inflation in a special class of non-singular black hole solutions, where a fundamental length scale explicitly appears in the metric, and the central singularity is avoided. We will see that these solutions can be easily reproduced in FR gravity. However, our argumentation will be much more general, and in fact will be frame independent. So I don't see. Okay, let us consider. You see all my screen. Sorry, one moment. Okay, so we are interested in a quite general static spherical symmetric space-time. Was a line element and Ricci scalar you can read in the first two formulas of this slide. Here, A is a metric function of the radial coordinate. K is just a topological parameter. It may assume the values of 0, +1, -1, depending on the topology, flat, spherical, or hyperbolic manifold. L is a fundamental length scale explicitly introduced in the metric, and we observe that R must be larger than L in order to preserve a correct metric signature. So finally, L is a minimal length scale for the radial coordinate, and in the physical descriptions we will expect it corresponds to a Planckian size. Obviously, the metric is free of the central singularity at R equal to 0. And with this kind of metric, we can, for example, describe static topological black holes whose horizons are located in the correspondence of the zeros of the metric function A. This kind of metrics may be exact vacuum solutions of a wide class of modified gravity models. And now we will see we will reconstruct an explicit example in the framework of FR gravity. FR gravity is the simplest extension of general relativity where the Lagrangian is just a function of the Ricci scalar. Obviously, all the models for which the Lagrangian and its first derivative with respect to the Ricci scalar are exactly equal to 0 for a specific choice of the metric admit this metric as a solution, as an exact solution. We are interested in the solutions which lead to zero curvature. The examples you see in this slide admit all the metrics, and in particular all the static spherically symmetric metrics which lead to zero curvature. The first model may support a sort of Starobinsky inflation. The second one includes one loop correction to general relativity. We can generate infinite examples. Now, if we come back to our metric ansatz with the condition r equal to 0, we get a second order differential equation for the metric function A, whose solution depends on two integration constants C and Q. The horizons of the metric are the non-negative real zeros of A times R minus L over R. There is a trivial zero for R equal to L, and all the possible zeros related to the metric function A. We observe that if L is sufficiently large, bigger than the zeros of the metric function A, this metric will describe a static wormhole. But if L is much smaller than C, this metric may describe a static black hole, and this is the case which is interesting for us. Finally, in the limit L equal to 0, we recover the Reiser-Nordstrom solution. We can also perform a numerical analysis of the result. For simplicity, we will consider the spherical case with k equal to 1. The equation r equal to 0 can be written as an hypergeometric equation whose solution is any linear combination of the two hypergeometric functions, which I call it B1 and B2. Here, the metric function A has been redefined as B plus 1, so the horizons of the metric are located in the correspondence of B equal to minus 1, and the functions are written in terms of a new variable x, which is equal to r over L. I don't know if r over L. So this solution is completely equivalent to the one that I showed in the last before. We may be interested in some physical descriptions, so as a physical solution, we may check for the one which makes the Euler-Schwarz space-time for large distance. In this case, it is enough to consider only one hypergeometric function. It means that only one integration constant, the mass parameter m, will appear in the metric, and is easy to check, to find that this solution rapidly converges to the Schwarzschild solution for large values of x if L is taken to be of Planckian size, as we expect, and m of the order of the mass of the Sun. We can also numerically check that there exists a critical ratio between m over L, for which if m over L is larger than this critical ratio, there are two horizons, an external event horizon and an internal Cauchy horizon. So finally, if L is a microscopic fundamental lens, this kind of metric may describe an astrophysical black hole with the presence of two horizons. The first horizon is an event horizon, is almost coincident with the horizon of the standard Schwarzschild solution. The second one is a Cauchy horizon. Obviously, by construction, this metric is free of singularity at r equal to 0. We may be also interested in the global space-time geometry of this solution. So we take the case where the metric function A has two distinct zeros, so it's for r equal to r plus and r minus, so which correspond to the two horizons. We may introduce the Tortois coordinate and the advanced and retarded time, and we can rewrite the metric in terms of the new coordinates. Now we are ready to study the maximal extension of the solution. The procedure is well known. We use the Kruskal coordinates. The sign of Kruskal coordinates U plus and V plus in the external region is fixed. However, since one of the both coordinates goes to 0 on the event horizon, or when the tortoise goes to minus infinity, and since the determinant of the metric is different to 0, we note that it's possible to analytically extend the solution beyond the event horizon. So we can redefine the Kruskal coordinates in the region between the event horizon and the Cauchy horizon, which are connected with the previous one through the surface of the event horizon. Again, one of the both coordinates goes to 0 on the Cauchy horizon. We can extend the metric beyond the Cauchy horizon. Until here, the description is the same as in the case of Reiser-Nordström solution, but now there is no time-like singularity, since the time-like singularity is cut away by the presence of a wall at r equal to L. Now I will show you the Penrose diagram of the solution, but at first let me say something. Let me say what happened when a particle hits the wall at r equal to L. Since the potential energy is proportional to the metric function A, if the fundamental length scale of the metric L is of the order of Planckian size and M is of the order of few solar masses, like in the description of the realistic astrophysical black holes, we see that the repulsive potential is so huge that the incoming particle should have a kinetic energy so large that it will not longer be a test particle. In fact, it's impossible that a particle will reach this wall. Here you see the Penrose diagram of the solution. It's very similar to the Penrose diagram of Reiser-Nordström spacetime, but we also see that the singularity at r equal to 0 is protected by a wall, the blue line at r equal to L. It looks something similar to the throat of a wormhole, but as I told just now, for classical particles, it's impossible to reach this point. So until here, I just show an explicit example of non-singular black hole solution satisfying a specific metric ansatz. Now I will come back to this general metric ansatz to discuss the stability of the solution near to the Cauchy horizon. So I will discuss the problem of mass inflation. This is an old problem. The presence of a Cauchy horizon may lead to some strong instability. At the origin of such instability, there is the exponential growth of the mass parameter of the solution due to perturbations under a cross flow between an falling radiation and outgoing radiation near to the Cauchy horizon. Mass inflation was first investigated by Poisson and Israel several years ago for the Kerr model and Reiser-Nordström solution modeled by Vadia spacetime in the framework of general relativity. Vadia spacetime is a non-vacuum charged spherical black hole solution with the presence of a poor flux of radiation. I will work directly with the metric. I will not consider the stress energy tensor of radiation on the basis of perturbation. As I told at the beginning of this seminar, in some recent works, it is argued that maybe mass inflation may be absent for regular black hole solutions. Now we will see what happened for our class of non-singular black hole solutions, where in any case we don't have the central singularity, but we also don't have a de Sitter core like for regular black holes. So we consider our general metric ansatz, which I showed at the beginning of the seminar. So we have a minimal length scale for the radial coordinate L. We suppose that the metric function A has two zeros corresponding to two horizons, an event horizon and a Cauchy horizon, and we also suppose, that is important, that only one mass parameter, or at least one integration constant, which may be identified with the mass of the black hole, appear in the solution, like in the explicit example we have seen for FR gravity. To describe the null geodesics, it is convenient to introduce again the retarded and the advanced time coordinates, and we will use the Eddington-Finkelstein coordinates for the metric. So infalling outgoing thin shell of radiation are described by constant values of advanced and retarded time U and V. Here you have the scheme of the process. An outgoing flux of radiation and outgoing flux of radiation collide in a region between the event horizon and the Cauchy horizon. The last one is located at V equal to plus infinity. The coordinates of the two sphere S of the collision are U0 and V0, and due to this collision, the space-time is split in 4 regions, and the 4 regions, this is an important assumption, the 4 regions are described by the same metric, but with different mass parameters MA, MB, MC, and MD. So, in fact, we are supposing that the radiation will increase or decrease the effective mass of the black hole. In particular, MC minus MB is the energy of infalling radiation, and MB minus MD is the energy of the outgoing radiation. MB is the mass of the black hole measured by an external observer before the infalling radiation will cross the horizon. So MB is the mass of unperturbed black hole solution. We also suppose that there are not singularity at the two sphere S. The key point of our analysis is the generalized DTR relation, which is a geometrical identity evaluated on the two sphere of the S of the collision, which connect the metrics of the 4 sectors between each others. In general relativity, the DTR relation can be written in terms of stress energy tensor, and its generalization to modify gravity is not so trivial. However, some years ago, an important paper of Brown, Mann, and Modesto showed that it's possible to derive the DTR relation, the generalized DTR relation, without using the field equations. And that's the reason for which we can take this relation independently on the theory, independently on the framework. 2 important assumptions are necessary. The first one is that MB is different to MD, just to have an outgoing flux of radiation. The second one is that MC minus MB, which is the energy of the infalling flux of radiation, is proportional to V to minus P, where P is larger than 12. This is the so-called Price law. And the Price law is valid, is far from the event horizon. The metric turns out to be, with good approximation, a sparse solution, like in the example we have seen for FR gravity. Now we will use the DTR relation for our non-singular black hole solutions. And at first, we will investigate the case where the fundamental length scale of the metric is different to 0, but much smaller than the radius of Cauchy horizon. The metric function A labeled by B corresponds to the space-time, to the unperturbed space-time. So it's possible to expand this metric function near to the Cauchy horizon by making use of the surface gravity, kappa minus. Now, if we work with Eddington-Finkelstein coordinates for radiation, we will have a relation between the R and the V. P is the advanced time. And finally, we can write the metric function A of unperturbed spacetime in terms of the advanced time, and we see that the metric function correctly vanishes when V goes to plus infinity on the Cauchy horizon. Now, the metric function labeled by A corresponds to the space-time after perturbation and can be evaluated by using the DTR relation. So, if we use the Price law and the result for space-time, unperturbed space-time we have seen in the slide before, we will finally derive an expression for the metric function A after perturbation, is the last row of this slide. which diverge in the limit where v goes to plus infinity. It means that the metric becomes unbounded as the Cauchy horizon is approached. In fact, the mass parameter of the solution will exponentially diverge, and in this case, we confirm the presence of mass inflation. Now we will see what happens when the fundamental length scale of the metric is on the same order of magnitude of the radius of Cauchy horizon, and in particular, we will consider the limit where the two quantities coincide. In this case, even if surface gravity is different, the result will be the same, and mass inflation will occur like in the previous case, unless we are in the extremal condition where L is equal to R minus. It means when the Cauchy horizon is located at the minimal length scale of the metric, in this case, the surface gravity will go to zero. And in this case, if we use the DTR relation, we will find an expression for the metric function A after the collision, which remains finite when V goes to plus infinity. In particular, we don't have the exponential term. We just have a term proportional to v to the second. We just have a term of v to the second, which is not enough to kill the term v to minus p larger than 12, which comes from the price law. So in this case, the metric remains finite, is bounded, and mass inflation will not occur. I remember you that in this derivation we used, we worked with the metric only. So all this discussion is independent on the model. So what I can say is that even in the presence of a Cauchy horizon, mass inflation may be avoided at least for some specific class of non-singular black hole solutions. And with this last observation, I concluded my seminar. Thank you very much for your attention.
Thank you very much, Lorenzo, for this interesting talk. So, do you have any questions? Just, it's not a question, Lorenzo, but what is the recent progress on FR gravity? I mean, because I'm very long time I am disconnected from the field. So now where is the progress? I mean, where is the edge of FR? Still, many people work.
As you know, FR
Yes.
is still considered as a viable alternative for the dark energy. If we speak about inflation, for example, about early time universe, we must consider some much more complex modification, which include the quantum correction model, for example, a quadratic term, so not only R square, for example. People study the FR gravity as a toy model since it's the simplest version of general relativity. Is a phenomenon. The only hope is to construct some phenomenological model, but with FR gravity only is not possible to take for a fundamental theory, of course.
You know, recently people get interested in the lower dimension gravity, and this we talked before together. An interesting fact is that, you know, this FR gravity appear also as an effective gravity theory for 2 dimension. In double dimension also it appears. It's very interesting. Very interesting. So I think it still is very interesting. I think it's the best candidate still after
really?
GR.
Oh, okay.
Yeah, in lower dimension also is yes. I think proportional to R square still is very important, not for inflation business, for the other things like this gauge gravity.
For other fundamental.
Yes, as a toy model. So, yes.